1074, number of submatrices that sum to target. Given a matrix and a target, return the number of non-empty submatrices that sum to target. A submatrix x1, y1, x2, y2 is the set of all cells within that. Okay, I mean that's fine. And yeah, basically, okay. Basically, you're just given the corners and you sum them, and if they all sum to a given target, yeah, then you just count how many of those are there, and there's no, I mean target doesn't matter, 300. So can you do? So how many possible squares are there? Well, 300 to the fourth, right? What's 300 to the fourth? Okay, that's 8 billion. That's a little tight. Okay, I mean, I think the first thing I would do is create kind of a lookup table. I'm not quite sure how I want to do it yet, but basically, yeah. So you want to create a lookup table so that, for example, you have maybe I need a whiteboard one of these days, but let's say you have a, maybe I will set something up actually, because this is actually kind of tricky otherwise. Do I have a paint app? No. I'm going to use this crappy paintbrush. Hopefully this is good enough. Hopefully I don't need to explain that much, so he's not using this. Hang on a second. Yeah. How do I get this thing up? Oh, there we go. Cool. Okay. It's going to be drawn pretty terribly, but I just got my point brush up. But yeah, but let's say this is your entire matrix. So what you want to do is kind of be able to look up the sum, like given another rectangle. Oh, I could change the colors actually. But let's say you want to calculate the sum of that rectangle, right? And the naive way is to kind of just do some n square e thing to go look inside. But if you have a lookup table where so you want to pre-calculate the sum such that you have a list of also let me know if this is showing okay. But you want to calculate such that like you have for each corner right here. Oh man, that is really high tech. But yeah, for every corner here, you want to calculate the sum from the origin. I guess 0, so that it's a result of a couple of operations, which is this whole purple square minus so the green cyane, I don't know, turquoise. I'm not good at colors, but so let's say that one. Is just you go to the purple minus is this working? Nope, wrong thingy. It's just that minus this, well, you could do yeah, this square and then minus this square, adding back another one, because as you can kind of see, it's double counting this other thing, which I'm going to draw in red. So so that's just like for adding operation, and that'll give you the value of x from the sum of all the cells in the turquoise. Man, I should have used the color. I know the color name of, but yeah, basically this region, right? Eep. Eep. Right. So that's what I'm going to do first, and pre-calculate that map. Okay, cool. So it's almost 300. Maybe that'll be. I even need to do this. Maybe not. Yeah, and you could actually do this pre-calculation recursively, or using the same kind of, and where's my paint? Same thing that we did earlier. Okay, fine, let's just initialize this. And then now, actually, I guess they could just I have to check the indices. Again, this is the double counting that we were talking about, and then now let's just print it out. Actually, I guess I could just put it out here. Whoops, sorry, it's blocking. You're right. Thanks, Purple Sheep. I thought I changed it, but I forgot to press the button. This thing is alright. Thanks. Okay. So now you could kind of double check this standard output. Yeah, because if you have, I mean, it's slightly harder to visualize, but if you have someone like this, you could see that the 3 represents these 4 elements. The 4 represents the 2 rows even. So it seems like it should be right. Okay. Just want to double check. Haven't done this in a while. Okay, so now I guess I have to double check some stuff. So I think like the strictest thing is like that is n4th, but it's or n to the 4th, but I think it's not quite n to the 4th, right? So in the sense that there is some constraint, so there is a big constant behind it. But so let me actually just want to double check my math. I think it could be I. So basically what I'm doing now is just trying to figure out the upper bound of, if I just do it naively, is this good enough? If not, then I have to, well, I have to think about another way to do it. What does that mean? I read the, oh. Man, my alphabets are not great. Because this is, it's end to the 4th isotonically, but okay. So it does 2 billion operation. Is that fast enough? 1 second? At the worst, what does this turn into? Oh, okay, well. So, and now we have to do 4 of these operations, right? Because now, is that fast enough? Let's just do something stupid like, because that's essentially what we'll be doing. 4 array lookups. Maybe that's will be more expensive. But still 1 second. But I don't know if it gets optimized out. So maybe I lie. But okay, well let's give it a shot. I don't know. 2 billion is around like the edge of what I would expect we could be able to handle. Even though this I think is actually whatever, but okay, these are the loops. So that's the minus. Oh, I minus 1, I think. Yeah, should be up. Yep. Minus some of. Nope. J minus 1 plus. Something like that. I mean, I have to check in, I have to check the array bounds, but I think that is reasonable. And maybe we could actually skip the array bounds if we allocate this a little bit better. Actually, I think I will do that. Okay. This is mostly to get the zeros, but I mean, you could probably actually put them into two linear arrays for loops, but I want to kind of go for it for now. And now you can actually optimize this. Though this isn't the slow part, maybe I don't need to optimize. Or at least not right now, but it's one line of code. Or like moving 2 lines. And then now I don't have to worry about it. Also, I forgot to use target. Why is this indentation here? I miss it. Oh. Oops. Did this work before? Oh, because now they should start at 1. Oops. Oh, because now this should be, yeah. Okay. So it's fortunate that this is at least right. But to be honest, I still don't, not super convinced at once in time, but I'm going to just submit it. It's probably borderline, but depends on the input. Well, I guess I couldn't say I'm super surprised, but still unfortunate, of course. Okay. Okay. Cool. But now we just have to think about another one. So I think that was a little bit insight with the lookup table, but still a naive algorithm, I would say. Ooh. Wow, so it wasn't even close. But now I have to kind of think about how else to kind of do I guess there's some observation that I could. I think I'm also torn between trying to solve this like in a constant way or just keep going. I think, for example, if this is there other negative numbers? There are negative numbers, so I don't know if we could. Oops. Yeah. So I'm also just wondering if there are any obvious constant factor things that we can do, but hmm. And my first question is like, well, we terminate early. Is that good enough? Like, if we make like a reasonable attempt to terminate early, but hmm. Okay. I'm just looking at the problem just to make sure that not missing anything obvious. This input looks reasonable-ish, I guess. I think my first kind of, just to articulate some of my thoughts is try to think if there's any ideal subproblems or some sort of ways that could help. Well, I think one of the earlier things I'm trying to do is also just whether like a constant time optimization is good enough, or do I really need to get this from n to the fourth to n to the third or something like that? And what would that mean? Um, what would that mean? And, and the other thing that I'm thinking of is that like, what does it mean for this to increment, right? I think this does way too many operations, but I don't know if that. I mean, I think I'm going to try it, but I actually don't know if this is uh, enough, right? Because when you add an extra L, uh, the difference is. So let me go back to the paint. Oops, nope. Nope. So I have something like this, and I add. So the next. Oops, that's not the right button. So in that case, the next column, all I have to do is just add this, right? So I don't actually have to do order operations necessarily. So maybe that'll speed it up. But yeah. Yeah, actually, this part I probably could have done better. I think I skipped too quickly, but okay, let me actually try to do that. Oops. Oh, what did I do? Oh. Oops. I guess I need another variable. Well, what's the delta? So that, given that we already have that, oops, what the hell? The delta is just I guess we could reconstruct our caching to kind of do it this way. Just trying to think if it's worth it. Because right now, I guess it's just actually just this minus this. Which we can cache. And we save one operation, which I don't know if it's fast enough. Okay, well. Guess we might as well try. Don't even know it's right. Oh no, I submitted it again by accident. That's what I accidentally did. Did I submit this now? Oh, I knew it wasn't clean enough, so whoops. Okay, so good news is it went in time, but it's wrong. Oh, I also have to subtract this part. Oh yeah, sorry. You're right. Well, yeah, now I'm back into the paint. So, but you're right. Sorry. I'll remember to do this. I just changed the codes very minorly for now. Wait, maybe I'll move it to the other side. Hang on. Okay. I need to subtract this, but so that's the same amount of operation, so that doesn't help, and it takes 10 seconds. So I probably need something more intense, it seems like. Okay, I guess my question is then, well, how do I get a lookup that is a little bit faster? Is there a subprogram that I could solve it? Am I and the other question is, am I just like kind of looking at the geometry too much? Can I yeah, because I mean, given this operation, can we actually look that up more, right? The hell? What am I doing? And whether we could, because each of these is 1,000, and and you could have 90,000 of them. Is that good enough? That's 9 million, 9D million. I wonder if there's a way to just dynamic programming this 90 million. And my code is pretty similar. I just need to maybe think about a symbol. Now I just have to think about how to kind of get to I need another way of thinking. Are these subprobs? What are the subprobs? To look at. Okay. Trying to think also like the entire time, like there's no ordering in the kind of how the matrix is gets constructed, in the sense that like there's no like there's no way to do like a binary search or something like that, because you don't have like that ordered substructure. So this is right, maybe, but too slow. Yeah, I think maybe I just need to be a little bit kind of smarter. Is that n cube? Yeah, maybe I could think. I think what I'm trying to think about it is, okay, so I did the naive n to the fourth. Okay, and I think the next step that I was trying to do is kind of think about kind of the two-dimensional case, right? Or sorry, one-dimensional case, right? Where let's say you have a line, a number line. I guess I actually didn't do that, but maybe I'll just put it here. Okay. I think the 1D one-dimensional corollary is much easier to think about. Where like, well, we have contiguous things. Well, actually, you could do that in linear time. Like, so the corollary is or the parallel of what I was doing is that, well, in 2D, or sorry, in 1D, the even if you had this kind of pre-calculation, the naive way is just an n square algorithm, which is n choose 2. You pick the two indices, and then and you have an or one operation that tells you whether the sum is equal to target, right? But and that's n squared. But you can actually do this in O of n, because if you have the two-finger algorithm, you could move the finger to the right. If it's bigger than target, then you move the finger to the left, and so forth, right? I think the only thing that's a little maybe trickier than for me is that because the numbers could be negative, so like it's not. Is it clear that we can move fingers? Because is that good enough? And contiguous. I guess that would work if it's all non-zero. Oh, sorry, if it's all graded or positive numbers, but because of negative numbers, I think that's a little, at least for me, a little tricky. Maybe. Can we convert this into a zero targeted number so that it works? That sums to target. So, I'm still right now. I'm still thinking about it, the 1D version, and then trying to think of how this line window works on that one. But maybe I'm missing something obvious. For this X. I'm still visualizing the 1D version. And maybe I don't need the full. My paint. Is that on 1D? Also trying to formulate just the 1D version so I can maybe get a better visualization. Because we have, let's say you have up to here. Let's put that is not what I meant to do. Which, let's say you have this. And this gives you some number x. I think I have an idea, but maybe the 1D version wasn't what I needed. Okay, I think I got the 1D version maybe. So I think what I want to do is, so this, you keep a running sum. Oh, I guess it doesn't show the thing that shows up here. So that will give you, well, actually maybe I could just do it in this window. So basically, let's say you have a list of number 1, 2, whatever. So you keep a running sum. So you have, yeah, and then you can actually do a lookup. So because you already know the running sum, what you actually want is given this number. I guess in a weird way, this actually ties back to the for sum a little bit. So okay, so let's say you're looking for the number. Your target is you go to, I don't know, 22, right? So actually, when you get to 28, your query is, well, how many numbers have I seen that minus the current sum gives us 22, which is 6, obviously. And in this case, it's kind of obvious. So this returns the result as you go to 1, and what's tricky now is if you have running negative numbers, right? So you have one. How do I want to do this so that it's negative numbers? Let's say you have -4. I don't know, something like that, right? Maybe. Okay. Actually, I guess I could even simplify a little bit. And I guess this could be -1s. But once you get to the last number on the fifth index or index 5, the sum is, you go to 0, and let's say your target is 0, right? This actually, what you want at this point is also, this actually gives you 3 count, which is, for example, yeah, I think I have a good grasp on this now, but I'm just not explaining it right. So let's say you have 1, -1, yeah. Okay, now let's say your target is 0, sum is 0, so you increment count. And then now you get to 1. Well, target is still 0, but the sum is, you go to 1. And then what that query now is you look through the previous array to see how many targets that are, sorry, how many previous indices in which gives you the -1, right? So the actual answer is one here. And then you do the same for here, except at this point, you actually have 2 different ways, right? Because you have the index that you have to index that's here, so that's 1, and then you have 2 indexes, right? So so in this way, you could actually find a 1D version of this 1D zero summing things in linear time. I forget about it. And actually, a lot of time, what people do is they use dynamic programming on the absolute values, and so I kind of forgot about this one. But yeah, so then and we sum all these 3, then you have 4, right? So I could even kind of, oops, then maybe I'll put this in the notes somewhere. Hang on, so that I could reuse this after I finish coding. So am I? Oh yeah, I guess I could just call it 1 index, 1 array, since. Right, so this should. Oh, well, I guess it actually added more stuff, but. So, yeah, so it should be 4, right? Okay. Okay. So that's the one. So I think we figured out the 1D case. So you could do it in linear time instead of n square. So how can you do this here, right? Going back to the paint. So I could delete this part. Okay, going back to the paint, adding. How do I explain this? Or maybe even just figure it out for myself. So for a given, okay, now I think I got it. Okay, so for a given x comma y, for x comma y, we have, so what we've been doing is we've been, is there a way to draw arrows? Not really, okay, fine. Oops. What we've been kind of iteratively figuring out this part, where, but like we just do it. So in this case, like this corner is ij, and in this corner is KL is where we have it, I think, in the code. And then we kind of iterate the j's or whatever, it doesn't really matter which dimension, such that, and then do the sum of the targeting, right? But actually at KL, we can actually, if we do something similar, we can actually just destroy a dimension by just looking up how many of these arrows, like how many of these arrows that do it in constant time, right? Like if we just have a lookup table of all the sums, then you could do that in constant time, and then that's how you would get to n of O of n to the cube, I think. Don't know if I'm explaining that well, but I hope that I explained the 1D version well, but the 2D version, I think maybe in code it'll be easier to explain. But basically, in this case, you iterate K, L, and one of I, let's just say I, and then on J, you get it for free with a lookup hash table that sums the number that sums to 0. Okay. But now we need a different hashing. Maybe we don't actually, but yeah, that's not for now. Even though it would cost us more operations, but it will still be n cubed, so I think that should be okay. Okay. And my naming is a little weird, so I don't want to do this. Okay. In this case, actually, I want the I and J's to be the ones in the upper right corner, and then this will just be on the rows. I think that should be fine. Oh, am I covering the code again? I hope not. Okay, I guess that's just covering the thing, but okay. And that's it. And now you add this column. You add sum of, and what the value for this column is just and there might be some off by ones, but I think that's we could figure it out. So now, so okay, so you start with the entire. Oh, now I'm using the thing again, so I need to bring it back up. Okay, so you start with the entire thing. Oops, what am I doing? You start with the entire ij, and then k. What's k? K is when you remove the bottom row. Okay. How do I express that in a good way? Oh, I guess actually. Oh. Yeah, okay. So actually you want I to be actually just okay, so this makes sense for now. And then for every row you actually subtract all this stuff. I'm spending too much time drawing, but that's fine. Which is okay. Just the entire thing. Is that right? I think so. Okay. Maybe. But now we have to look up Well, how many cases are there for? Yeah, my index is maybe a little weird. Looking at the 1D case for inspiration, just to make sure. Maybe that's why I didn't articulate it well. I'm not 100% sure on the 2D core. I think of this stuff. But then how do you get the number of count that we have in maybe the subtraction as well? I need. Okay. Is this better? Now we have that. Okay. So now we have, and given this chunk, so these are my i's and k's, and then now we could just build. Okay, now I could do it. Oops, maybe do a different color though. And then now I just go up this way. Okay. So let me go to 0. Now you add the value of the new row. What's the value of the new row? I is the bigger one. Okay, I mean this is what we had before. But okay, so that's the value of the new row, and then now we can hash it. Oh man. In that case, I need to do a language that has a hash table. So now we look for target minus s. There's something like s minus target. S target minus s. So something like that, and then hash some s. increment it. Okay, and I think this is mostly okay. Hesitate to say that, but I don't have a hash table in C. Let me change. Let me copy and paste this into C++ real quick, so I could use set. STL. Was it? It's just map, right? For a while. Yeah, okay. This technically is not defined, but that's maybe fine. How do you get it? That's again, my C# is leaking, but then not because oh yeah. Yeah, that's unfortunate, but that's fine. It's a good start. My indices may not be 100% correct. So oh no, this is a different one. No, this should maybe be right. Well, like it should be correct. Curses. Oh, actually, never mind. I thought I saw something, but just had him print one of the values. Okay, so that seems right. That's fair. Second one's also fair. Running sum is 0. This one should be 1 for -1. Is that true? Oh, yeah, maybe this is S minus target actually. Because actually you don't, yeah. Well, I mean, one minus. No, the other one was right. No, that's weird. Man, okay. I think I'm on to something, but now I'm having a off by 1 somewhere. I think this should be more right, but okay. Let's take a look. I think it's just that we don't keep track of the 0 index. This will crash. Yeah, I think we don't keep track of this 0 index, that's why. Okay. Maybe? What am I doing? Okay. So so put the first one. Okay, the sum is 1. Okay, that's fair. That is actually not true. So 1, okay. And the -1. Oh, I lost my other C code. Okay, fine. Maybe I just need to. Man. This one looks for -1. I think that's more reasonable. Okay, doesn't find any, so it keeps going. And then the second column goes to -1. The sum is the running partial sum is 0. Yay! But then it doesn't put anything in. So I mean increments here, but maybe I just need it. This is that necessary? Maybe I just. This is. That'll give us the base value a little bit better, but oops. Some no columns. And there's 0. On all the sums that are previous to this. Is that reasonable? I don't know. But with 1, there's no good. I think that's fair. 2, also 1. I think that one's good. But at index 3 is where we have issue, because this 1 should match up to -1. Why don't I get that partial sum? Or how do I get that partial sum? So 1, do we look up -1? I think maybe I just try to simplify this a little bit too much. Okay. Because you have 1, -1, 1. So what you're searching for is target. Actually, where target is. Well, let's say we're searching for 0. You're actually searching for 1. And I keep on confusing back and forth. Maybe it's like you're not looking for stuff that you're not looking for the sum such that they sum together is target, you're looking for. I think that's what this problem is why this one is giving me little issues because in this case, I think what you want to do is. Maybe I go back to the painting. Am I on the painting? Okay, the painting is on. I think what I was doing was that in the 1D version, let's just say this is the number line or the index for the arrays. And I use a test case that's a little confusing for me. But let's say you have here, and your running sum is some number. I don't know, some number sum because that's what we s. What I was looking for was kind of the numbers that sum up to negative s. But actually, you want all the previous cases, and there could be multiple, where it sums to s, because that means, because if this is s, and this assumes target is 0, because if this is s, that means all the in-betweens, use another color, that means, no, that means the in-between is negative s, because this s represents the sum between, actually represents this range, right? Okay, and I think I kind of mixed it up a little bit, and that's why in that case, in that way, it is not similar to the for someone or to someone or whatever it is. Okay, if that works for my weird case, let's try the other test example cases first, especially since I've only tested on essentially one-dimensional arrays. Ooh. Well, I got one problem right, but it's going to be a long night. But okay, now let's break this down a little bit more. Then I guess I need to copy and paste. Output is 8. Oh man, this is going to be a long debugging session. Okay, fine. Target is 0. Why did I get 8 then? Yeah, you're right. This should be a trivial case where only 4 submatrices or whatever, but so that is just the 4 corners. So 1, 1. That's right. So far so right, but no, this can't be right. Okay, let's take a look into why. Because that's representing the rows 1 to 3, one indexed, and J is 0. And then the sum should be I'm not using K, am I? So I think I just have a so there's something weird about how I'm doing it because it's not counting the right arrays. Okay, that's fine. Or at least it's debuggable. So that means if I sub j is this corner. So here minus this chunk minus okay, so this chunk minus this chunk. Okay, so that's just one row. And then for given j, also my diagram is just really wrong. That's why I'm confused. It's actually you're sweeping this way for every I. Wait, is that right? No, that's not right. But it is just still really wrong. Okay. Ij minus sum of fossil group minus so this stuff. This is not right, is it? This one maybe is right. Yeah. So the delta is just ik. I did not do my pre-calculations correct or optimally. That doesn't make sense. Well, that made it worse. But okay. So you're going from this should be k minus 1, I think. Okay. It's a little bit later in the day. Maybe I'm a little tired because this I was not defining what I was trying to do very easily. But even though I knew what I wanted. It's just I couldn't define it quite well. Okay. Now let's try that monster case. Uh-oh. Oh man, really? Is this expensive? Maybe. Huh. Should be n cube. So, something like that. Hmm. Am I thinking of a different map? As it contains. Also maybe put on the thing bit. This isn't even right, but wait, what? Am I doing this well? Am I doing something weird? Cube should be fast enough, right? Or am I, oh, well, this does one, but I think this is similar to what they said, but, plus 64 minute. How come there are no expectations? Let me wonder one more times. That was roughly what I remembered. It showed up earlier, but I don't know. Might as well take the extra 10 seconds and check it out. If not, I'll just submit it, I guess. Oh, actually, this will actually tell me. That was a mask case. It doesn't actually tell me what the output is. could have sworn it showed me earlier, but maybe it is just, I don't know. I'm just going to submit it. This seems roughly right. Okay, cool. Yeah, that took way, well, I was going to say that, well, it definitely took way longer than I would have liked. Um, hmm. And look, I have 100% memory usage. Better than 100%. How do I feel about this? Well, one is that this is probably a little bit harder than a, an interview should have it. That's not, though I think I was just a little, we'll blame it on a little bit on fatigue as well, because I think I spent like way too long just debugging this particular thing. Even though I knew I wanted K, I'm just having issues visualizing it for a little bit. But still, yeah, I think it is a little bit too time consuming, maybe to figure out on the fly. Maybe not. I don't know. I want to say it's a little tricky. Yeah, it's very involved. It's only 50 lines of code. I think that's my only hesitation in saying like I feel like if you, but I think that's kind of my problem with it is that like, yeah, if you already seen this problem, if you already know this problem, is then like it's very straightforward, I think, and it's 50 lines of code and it's great. Even though there may be a lot of off by one potentials and something that I have to look into again. Like I don't know if why am I? Yeah, well, yeah, I definitely does this work? If I, but but anyway, yeah, it's very involved problem. I think adding the extra dimension doesn't really add that much to the problem, except for it asks a little bit more. So I think I like the problem. I think I definitely like the problem as an interviewee. I like solving it. I just don't think it's a good interview question. It's a little bit on the harder side than I would normally expect or reasonably expect. I would say. That said, I think the 1D version I could maybe reasonably expect that to be on interview difficulty. I don't know how much of it is that I'm biased by this problem. I think the only issue is that again it's very binary and that like if you know the trick then it's going to be easier. If you don't, then it's going to be a little bit hard to kind of figure out from scratch. Maybe I have to think about this problem a little bit. Maybe you could give hints such that because I think it is a cube problem, the 1D problem. Though again, if you have, if you know it's a little trickier, you know it's a lot easier. But I guess you can say that about anything, right? But yeah, overall, generally, I don't think I would expect this level of difficulty on an interview problem. Uh, but maybe I don't know. Maybe it will still be on the hard side. But I think the 1D one, I think it's reasonable. I would maybe actually even try giving it, but there's a little yeah, because it does use some of the very fundamental data structures very well in ways that just in general. There's you do a lookup table, similar to sum, which everyone laughs at as being easy. So you have that going on, but you use it in a way that requires some pre-calculation of what's it called, partial sums along the way, which is I think a clever usage. I don't know if I've seen it. If I have, I haven't seen it in a while. That obviously because it took me quite a while to. But yeah, overall, I mean, I think it's a fun problem. It's a really involved problem, but it's like 50 lines of code. You got it right, and yeah, I think this is cool. A little bit of a postmortem. I think. Looking back a little bit, I was definitely a little bit slow on just getting the indices right. I think if I could do it again and should do it again, especially after kind of figure out the 1D and then extending it to 2D, I think I would have maybe recalculated. I think what I did was that I tried to keep too much from the old code, which is sometimes like what's it called, a sunk cost fallacy. I think what I should have done is just throw away the code and write everything from scratch. But And then maybe I could have that better thing because I didn't really need the whole full matrix sensitive. Because some I could just maybe do it in a smaller way, but I don't know. I think, and also just if you kind of look back at the tape, I took way too long to kind of correct just this minor thing from I to K. I and I think that kind of speaks to needing performing optimally sometimes when you're tired. And I was doing this 3 hours straight. Is that you just need to kind of take care of yourself both body wise and mentally, so that you can when you do an interview you'll be performing close to optimal. I think that's all I have to kind of add to this. Yeah, I mean I think I like this problem. It's not too difficult. I think it took me a while, but I just struggle a lot with the implementation, and I think a lot of that is not something that I would expect myself to struggle. So I just need to kind of chalk it up to being able to perform optimally when I need to, and not just yeah. Oh yeah, one thing that I want to point out is that I did do an optimization because it was timing out. Is that I did add this line here, line 41. Is because what happens, and this actually requires just like knowing your language in general. But because I was just doing it without the checking to see if it's in the array, in the hash table, or hash map in this case, it actually creates an object every time I do something like this, and that's why when I added this line, it was able to kind of one in time because it probably wasn't creating I don't know 400 million objects or whatever it is. Was it 300 cube objects? But yeah, cool.